Welcome to Chapter 10, Section 7, Inscribed and Circumscribed Polygons. In this section, our goals are to recognize the difference between inscribed and circumscribed polygons, apply the relationship between opposite angles of inscribed quadrilaterals, and identify the characteristics of an inscribed parallelogram. So let's start things off by taking a look at these two diagrams and noticing the difference. Well, both diagrams show a square and a circle. The square is red, circle is in black, but the difference here is what's inside of what. Okay, the square is inside the circle in the first one, and the circle is inside of the square in the second one. Well, these two ideas have specific names called inscribed and circumscribed. We use these adjectives to describe polygons or circles dealing with their location about or inside of another polygon or circle. So we describe something that's inscribed if all vertices lie on the circle. Okay, so this square is inscribed in the circle, and the center right here we call the circumcenter. Okay, and we'll talk about why in just a moment. But if a square is inscribed, it is inside the circle. So this is the square is inscribed in the circle. Well, if a square is circumscribed, then each of the sides is tangent to the circle. So we have these points of tangency about the circle, and our square is outside. So we have 4 points of contact, 4 points of tangency, and this center we call the incenter. Now, these may seem a little backwards, but the center refers to the circle. Okay, it's the center of the circle. So in this case down here, when a square is circumscribed about a circle, the center of the circle is inside the polygon. It's inside of the figure here. So our circle is inside, so we call that the incenter. Up here, the circle is actually being circumscribed about the square, where the square is inscribed in the circle, and we call that center. So let's take a look at Theorem 93. In Theorem 93, we're told that if a quadrilateral is inscribed in a circle, so inscribed meaning the quadrilateral is inside the circle and the vertices are on the circle, its opposite angles are supplementary. Okay, well, let's prove this to ourselves. Let's say that this angle right here, we'll call it angle 1, and this angle we'll call angle 2. Okay, so using some information that we had from a few sections ago, we know that when an angle has its vertex on the circle, such as these two angles do, the angle measure is just half the intercepted arc. Well, for angle 1 here, the measure of angle 1 is just going to be half of the measure of the blue arc. Well, let's call the blue arc x. So if the blue arc is some x degrees, the measure of angle 1 is equal to 1/2 of whatever that x is. All right, and with the same reasoning, we can say that angle 2 is 1/2 of the yellow arc. Well, the yellow arc, we don't want to call it another variable. Let's call it something in terms of x, and that'll be 360 minus x. Now, why is it 360 minus x? Well, the blue arc is x, the yellow arc and the blue arc together complete a full circle, and every circle has 360 degrees, so therefore the yellow arc has to be 360 minus whatever the blue arc is, x. So then if this is the measure of angle, or excuse me, if this is the measure of the yellow arc, the measure of angle 2 will have to be half of that. So it's 1/2 of the quantity 360 minus x. And if we distribute the 1/2, we see that the measure of angle 2 is simply 180 minus 1/2 x, or we can exchange that and say that it's 180 minus the measure of angle 1, which shows us that angle 1 and 2 are supplementary. All right, so this happens for any quadrilateral that is inscribed in a circle. We know that opposite angles have to be supplementary. So angle 1 and 2 have to add up to 180, and then we call angle 3 and angle 4 here, they also are supplementary. Okay, let's take a look at Theorem 94. We're dealing with a parallelogram that is inscribed in a circle. So parallelogram, remember, it is a quadrilateral, but it's a special quadrilateral that has opposite sides parallel, opposite sides congruent, opposite angles are congruent, and diagonals bisect each other. Now, using that idea of a parallelogram and Theorem 93, we know that this must be a rectangle. Well, how do we know? Well, opposite angles, we know of a parallelogram, are already congruent. So this angle has to be congruent to that angle, and this angle has to be congruent to that angle. Well, we just learned in Theorem 93 that opposite angles inscribed in a circle are going to be supplementary. Well, if these two angles are congruent and supplementary, then they have to be right. So if A is a right angle, and B is a right angle, and C is a right angle, and D is a right angle, then this must be a rectangle. And that's a little informal proof of why Theorem 94 is correct. Now, Theorem 94 lets us conclude a few things here. So, given that we have a parallelogram inscribed in a circle, we already know that the parallelogram has to be a rectangle. So what does that mean? If our vertices are A, B, D, and C here, and we have center O, well, we can conclude a few things. First, BC and AD are diameters. So BC and AD are both diameters. What does that mean? Well, that means that they have to go through the center of the circle. So if we don't know the center of the circle, we can find it by inscribing a rectangle inside the circle and then finding where the diagonals cross. Okay, so BC, AD have to be diameters. O has to be the center of the circle. That's where our diagonals cross, and it has to be the center. That's the only way that a rectangle can be inscribed in a circle, is if O is at the center. So that means that OB, OA, OC, and OD are all radii, and we know they're all congruent. And we can use Pythagorean theorem to say that AC squared plus AB squared is going to give us CB squared. All right, using the Pythagorean theorem to look at this right triangle right here. All right. Now we can use that same scenario to find AD, saying that AB squared plus BD squared will equal AD squared, and we can. So let's try an example here. Let's say we're given that ABCD is inscribed in circle P. So P is the center, the vertices A, B, C, and D are all on the circle. And we want to prove that angle A is congruent to angle BDE. So we have this angle over here, angle A. We want to prove that it's congruent to angle BDE. All right, well, let's try to set up our proof here. So we don't have much given. In fact, we only have one piece of information given to us. So we can just state that piece to start. Say that AB, and this really should be ABDC, is inscribed in circle P. And that is given for us. Well, in step 2, we can say that angle A is supplementary to angle BDC. Now, why can we say angle A is supplementary to angle BDC? Well, because opposite angles of an inscribed quadrilateral are sup. All right, that was Theorem 93 that we just saw. Opposite angles of an inscribed quadrilateral have to be supplementary. Okay, well, if these two angles are supplementary, we can also say that CDB is supplementary to angle BDE because they form a straight angle. So we can just say that angle BDC is supplementary to angle BDE because they form a straight angle. All right, if two angles form a straight angle, then they're supplementary. And then finally, we can say that our angle A is congruent to angle BDE because if two angles are supplementary to the same angle, then they are congruent. All right, so that's a nice little 4-step proof. We're going to continue working on stuff in this section. If you have any questions, please come to me and ask. Thank you.